I think it's going. Okay. And that's something that I'm going to do each time with recording a meeting. But so generally I'll remember, but as some of you know, sometimes I do forget. If it seems like I'm starting class and I haven't actually recorded, if you can see in Teams it's not recording, then please remind me right away, because otherwise it'll just drive me nuts that I missed something. Okay, so, well, welcome to Math 610, Numerical Linear Algebra. It's nice to be starting a semester where, yep, I know, well, see, I know all of you, and 9 out of 10 of you have, actually, no, everybody has taken a class from me at one time or another, so that, at least from my point of view anyway, reduces some of the awkwardness. Well, okay, it doesn't get rid of it entirely. We are starting a semester, and the first couple weeks of any class are always awkward. So we just try to get through that. Also, as unlike some professors, I don't have any, rules about, camera use or anything like that. But I do appreciate that some of you do have your cameras on, because I've had classes where I just see a sea of black squares and people's sore pictures, and that gets a little depressing. So thank you for making this seem somewhat more class-like. Thank you, Chandler. Okay, so we're gonna get through the typical beginning semester syllabus day stuff, and then I do actually plan to cover some things today. I might have put too much on the plate, but we'll just see how that goes. We have a new version of Teams now. Take some getting used to. All right. Okay. I just want to make sure, because some weird message popped up. Can you all see my screen? In particular, Canvas.
Yes, I can.
Okay, good. So actually going to have everything for the class, or pretty much everything, posted in 2 places. So here we have my Canvas setup. So links to all class meetings we posted here. The meetings for the current week will always be at the top, and then older class videos will be at the bottom. This goes to the discussion, which in this case just has a link to this Teams meeting. But after class, not right away necessarily, because I have another class after this one that several of you are in. But later that day, I will post a link to a video. Also, any files that I use, like my notes, or if I do anything in Matlab, that'll be posted here also. Okay, all the homework assignments are here. So we have 2 types of assignments. So we have Canvas quizzes, which are the concept check questions from a book. Okay, here's a book, my book, that I believe you've all used at one time or another for something, for 460 or 461 or 655 last semester. So the concept check questions are taken directly from the book. So enter your answers to in Canvas. If you've taken 560 or 561 from me last year, you've done these kind of quizzes already. And then we have homework problems from the explorations that are in the book, 4 assignments altogether. So the grading is very simple. This is coursework the whole semester, and I'll be just giving each one of these grand total of 9 assignments equal weight. Okay. Okay. Now, I also have this site. And when I sent the welcome email a couple days ago that all of you should have received, I sent a link to this site. So these are kind of sites that I've been maintaining for my classes ever since even before I came to USM. So if you go to my main web page under courses, everything is here. So you even have like older versions of 610. I just realized this is the 9th time that I'm teaching this class, so all of those old versions are here, and so you can see a duplicate of a syllabus. There's a syllabus document posted in Canvas. All of that same information is posted here. Okay, and the usual stuff that's supposed to go in the syllabus. And then all of the homework assignments, except for the Canvas quizzes, all of those are posted in here. Oh, I just realized that I meant to put something here, homework 5. Totally forgot about that. Yes, so there will be 10 assignments altogether. But you can see a full list of problems, and this basically mirrors everything that's in Canvas. I have on the resources page, these are my notes from 610, and this is sort of like a precursor to the a big portion of a textbook that has everything I've covered in 610 and related topics. So it's quite a smorgasbord of numerical linear algebra material, even more than is necessarily actually covered in the class. But it's been checked a lot more thoroughly for the actual book. But just want to mention that's there. Okay, and all right. I just realized that I've had this cats page on my site for years. Unfortunately, these cats are no longer with us, but as of Christmas, this past Christmas break, we have a dog. So we'll have to add a page for her to this. Okay, so that's the resources that I have. Okay. Now, and what I'll be doing during class period is here I have material stripped down from whatever section we're going to cover each day, because as you can see on the schedule, you can tell what I'm going to cover each day, and unless something really odd happens, like a natural disaster, this will be what I'm covering each day. So I'll be taking those, and then I'll be going through them during class, and also editing them, like for instance, based on any questions I get during class. So then the edited version is what I'll post in Canvas later that day. One thing I want to mention about the schedule. Okay. So here, this week coming up, the second week of March, I'm making it an unofficial spring break. So my thinking is, university is not having a spring break in their schedule like we usually do because of a pandemic. We want to end the semester earlier. So instead of having it spill over to May, it actually wraps up April 30th is when the last day of finals. And so I can understand that that reasoning there, but by the time we get to this point of semester, several weeks in, I feel like all of us will need some kind of break. That doesn't change just because of this pandemic altered schedule. So essentially, we are going to have one. So what that means is class during this time, I'm not going to be covering anything new. Now, since I'm obligated to actually have a class meeting, I will be here. So if anyone wants to come and have homework questions, it's basically an office hour. Then you can do that. But I will not have anything due during this time. So if you want to think of it as just a break from class, you certainly can. And I'll be doing, and those of you who will be taking my other class, 517, I'll be doing the same thing there during the same week. So to the extent that possible, we are having a spring break, dang it. Now, but just like unfortunately, for those of you who are teaching or whatever other classes you're taking, those are still going on. But I figure if I can give you a little bit of relief, and I'm pretty sure I will need it too, then that's what we'll do. Okay. Now, before I get into material, wait, let's see, there's something in the chat here. Oh, okay. You're welcome. So, now, whoops. Okay. Now, does anyone have any questions about how the class will be run? Okay. Well, yeah, there's really not that much to it. It's like, here's the assignments, go. Okay. So now we'll get into the notes. So out of curiosity, especially those of you who are teaching, so some of you may have had your first class already or will be having it later today. How many of you, even though we're just starting a semester, we're halfway into the first day, how many of you have already had unexpected crap come up? Okay. No.
I mean, the semester didn't even start for me, and I had a huge major family emergency that was unexpected that we're still dealing with.
Oh, ugh. Well, I hope that hopefully that gets resolved soon. Because, yeah, because now you have all this other stuff going on. So if you've done, yeah, literally 10 minutes before this class was to begin, my plan was to open these notes in this program, Bacoma Tech Word, that I believe all of you have seen me use in some of our class, where I edit LaTeX code on the fly and renders immediately, which is better than being subjected to my handwriting on the board. That I launched it and it wouldn't run because I got a new Mac over a break, and so the previous version of Bacoma Tech Word would not launch, and to did upgrade it. So I had to hurry up and do that because like if I didn't have that, it's like, well, how am I going to run class? I'd have to do it very differently, and no idea how. So I mean, it all worked out in the end. And there's been other things going on too, but yeah, it's just gets the adrenaline flowing, so we can be in the right frame of mind for class. Okay, now those of you, this material, first chapter I covered, chapter 3, which are called direct methods for solving system linear equations, AX equals B. This material was covered in Math 561, which some of you took last year. So that part will be reviewed to those of you who are taking that class, but I figure you've had a year to forget it. And figure review is a good thing. What have we here? Samson, I see a hand up.
Yeah, I was going to ask about that because I went through the assignments, the homework you assigned, and realized that most of it I have done from 561. So I was thinking maybe I could just turn that in.
Yeah, I forgot about that there would be this duplication of those problems. Well, if you got a perfect score back then by all means, and If not, then you should fix that up. So, yeah. These classes, 610, 561, are where I have often goof of homework. For instance, I've had this tendency to accidentally do homework problems during class from time to time. So I've tried to cut back on that. So, yeah, I guess I really can't stop you from doing that. So, I would suggest you give it a look over. Just
Yeah.
because then when we get into chapters 4, 5, and 6, and build on that. And the thing is, chapter 5 is on iterative methods. There were some iterative methods covered in 561, but we look at entirely different iterative methods here. So really chapter 3 is the only overlap. So at least you'll still get lots of new stuff this semester, just not yet. Also, of course, we will use Matlab for some problems. If you were in 685 last semester or 560, 561 last year, then you've had Matlab exposure, and I believe everyone here is in that category. I think I've taken at least one of those classes. And here, we don't have time. We're just assuming you are up to speed with Matlab, and we're just diving right in. If you're rusty, then it's something that we need to deal with. But the problems will be a mixture. There'll be some Matlab problems and some worked out on paper. Okay. Now, okay. So the much of a course, not all of it, but much of it, is about solving system equations, system linear equations, AX equals B, where we have matrix A and right-hand side vector B, and X is what we are solving for. And so my first editing here. Okay. So in this chapter, we will be all about direct methods based on something you've seen before as this Gaussian elimination for solving AX equals B, as opposed to iterative methods, which are in chapter 5. Also, we're interested in this chapter. We're interested in the case where A is a square invertible matrix, whereas in chapter 4, we will be dealing with least squares problems, where A is no longer assumed to be a square matrix. It's m by n. And generally, we look into the case where it's more rows and columns. In other words, the system AX equals B is overdetermined. There may not be an exact solution, but we try to get as close as possible to a solution in some sense. And then we'll be looking at some related problems there. So chapter 3 is in direct methods and least squares problems, and then iterative methods in chapter 5. In chapter 6, we'll deal with eigenvalue problems, methods for computing eigenvalues, also singular values that are related. And then since machine learning, statistical learning rely very heavily on numerical linear algebra, I'll be discussing that at the end of a course. Okay, so that's a very brief outline of what we're seeing this semester. Okay. Okay. Yeah, there's definitely no expectation of retaining information from last year. So I want to make that clear. I've found that, especially at USM, uh, teaching is a whole teaching classes at a variety of levels like I do is a whole lot easier if you simply assume that while the students may have taken prerequisite courses, that they remember nothing from them. Um, but yeah, it's somewhat like riding a bicycle. It's no, it does come back after some time, because it's stuff you have seen before, just a little bit rusty, and it's only slightly less injurious. Um, so um, yeah, um, yeah, so for chapter 3, I'm going to just go through all the things. I may end up skipping certain things that I don't really need that I did cover in chapter 3, but that's the only real difference. Okay, so see if I can get through these 8 pages in 50 minutes. But that sounds scary. But we'll see how it goes. All right, if not, there's always Monday. So the idea is we want an algorithm for solving ax equals b for any square invertible matrix A. We want to address the general case. So when you're designing numerical methods for any problem, not just this one, there's 2 questions that are worth asking. Are there easy cases where are there types of matrices A in this case where we can easily get to solution X? And then once we've examined that, then is there a way to reduce the general case to one of these easy cases? So this is a good 2-stage process for designing numerical methods. And this is useful beyond linear systems. As an example, in 560, which some of you have taken, or I covered the same thing in 685 last semester, say numerical integration. Are there functions that are particularly easy to integrate? Yes, polynomials. So based on that, how do you reduce a case of approximating the integral of a general function to the case of polynomials? The answer is polynomial interpolation. So this is a good frame of mind to have when designing any numerical method. Okay. So what are systems of equations that are particularly easy to solve? We have these 3 that all have one thing in common, that you'll have at least one equation in your system that only depends on one unknown, because the system of equations ax equals b, each equation can depend on all n unknowns, so it's difficult to solve for each of them. But if you have an equation that depends on one unknown, you just do some algebraic manipulation, and bam, you have its value. So anytime we can be in that situation, then we have a system that's easy to solve. So we have 3 different types of matrices. So where A is a diagonal matrix, or an upper triangular or lower triangular matrix, that puts us in a situation where we can just proceed straight to the solution. Now I'm going to talk about all these in detail in just a little bit, but the thing to keep in mind is how you characterize a matrix as diagonal or triangular in terms of the entries. So here we have entries Aij, where, and I'll remember, you haven't dealt with matrices in a bit. The first index is always the row, second index is always the column. So when the 2 indices are equal, that means you're on the main diagonal that goes from upper left to lower right. So if those are the only non-zero entries, then it's a diagonal matrix. Upper triangular, if the entry is 0 whenever row is greater than column, then it's the upper triangular matrix. If the entry is 0 whenever the row index is less than the column index, then it's lower triangular. These characterizations are helpful to remember in any proofs, for example, involving triangular matrices, or designing algorithms involving triangular matrices, because you're able to make these assumptions about which entries are zero based on the indices. So it's good to remember how to characterize these types of matrices based on how the indices relate to one another. Okay. All right. So simplest system of all, a diagonal system. So you only have these non-zero entries here along the main diagonal in matrix A times x is equal to b. So if you carry out matrix vector multiplication, so remember how matrix vector multiplication goes, I go across this row and down this column, multiplying corresponding entries and adding them all up to get the first element. And then I go across the second row and times this column, multiplying corresponding entries and adding them up to get the second element, and so forth. So when I carry out that matrix vector multiplication, this is what I get. I just have a diagonal entry times the corresponding entry of x is equal to the corresponding entry of b. So these are my equations that are trivial to solve. I just go ahead and divide by these diagonal entries, which would therefore better be non-zero, and there I have my solution. Okay. So it only takes n divisions for an n by n matrix, and then we have our solution. Okay. Now, so what I could do is I could describe this process as an algorithm. There's not much to it, certainly. So I just have, so if I'm implementing this in Matlab, I'd have a for loop that would set each element of x equal to the corresponding element of b divided by the corresponding diagonal entry of a. Now, one thing that's worth pointing out, it seems like a trivial thing here, but it will be relevant later. I can solve these equations in any order. That means I can solve them in parallel if I have a computing power to do that. This is important now because there'll be other classes of matrices where, yes, we can solve ax equals b easily, but you must proceed in a certain order for that to happen. But here, that's a non-issue. Okay. So n by n system, we just have n operations in total. A quick way to describe the efficiency of an algorithm as a function of the problem size, in this case n, we have n equations, n unknowns, is how many operations does it take as a function of n? Is it on the order of n squared or n cubed? That exponent makes a big difference in terms of the efficiency. But here it's just n. All right. Now, the next case that's a little more complex is upper triangular systems. So here I have a matrix like this. This is where upper triangular gets its name. But everything down here where I have blank space, that's assumed to be 0. So anytime the row index is greater than a column index down here, it's 0. So then, how do we solve a system like that? So I'm going to first do an example. So here we have an upper triangular system. So the matrix of that system would have 1, 2, 1 in the first row, and then -4 and 1 in the second row, and then -2 in the third row. But these entries down here are 0 because they don't have nothing multiplying the unknowns here, like x1 in this case and x1 and x2 in this case. So how do we solve a system? Well, here in this example, it's easy to see how to proceed. We can just start with this equation because we can just go ahead and solve that right away. So here we just go ahead and divide. So at least we have x3. But then what you can do, what about the next equation up? It depends on x2 and x3. But we know what x3 is, so we substitute. So we go ahead and put that value in here. And then we can move this to the other side and then divide by -4. And now we know x2 and x3. So now we get to the first equation, which is the last one we handle. It depends on all three unknowns, but 2 of them are known. So we go ahead and substitute these in here. And then we can move these terms to the other side and get x1. So we start out with the last equation involving only one unknown. And then each equation in turn will involve only one unknown after we've substituted in the values of everything we've computed up to that point. So we like to get, so we can see intuitively, like on paper, how we solve such a system once we have it. But now we want to have an algorithm, something that we could implement in Matlab, for instance. So what I'm going to do is work through the same kind of system, but a general case. So I can see formulas for the entries of my solution x. So if we carry out the same operation, so here we go ahead and divide and get x3. And then, since we know x3, I can take this equation and isolate x2. So if I go ahead and do that, so I've substituted x3, moved this term to the other side, and then dividing by the coefficient of x2, the a22, and we have this formula here. And then I do that one more time. So now I know x2 and x3, so I can substitute these in here, move these terms to the other side, and then I'm dividing by the coefficient of x1, which is a11. So if we look at the formulas for a solution, unfortunately I can't fit them all on screen at one time, but here we just have a division. And then here we have subtracting certain terms off from the right-hand side value, and then we divide. And notice that the number of terms we subtract off keeps increasing as we go up through the list of equations. So here we're not subtracting off anything, then one term, then two terms. So that pattern is something that we can exploit to design an algorithm. So what we can do is, here's a formal algorithm here. We're solving ux equals y. So I've changed my notation for the upper triangular case. So u is assumed to be an upper triangular matrix. Y is our right-hand side. So what do? I start out with the right-hand side value. So I set my solution x to be equal to the corresponding value of y. And then I have to subtract off these terms. Now, which terms are they? Let's look at the indices. Here I'm dealing with the second equation, and I subtract off a23. Here I'm dealing with the first equation. I deal with entries a12, 13. What's the pattern here? First, notice the row indices, 1, 1 in this case, equals the index of the unknown I'm getting. Also, notice the column indices are always strictly greater than the index that we have here, which makes sense because if we go back to the system, we're trying to find these unknowns, x1, x2, x3. Any terms with greater column indices in that row are the terms that we have substituted in previously found unknowns and then move them to the other side. So we're going to subtract off uij, where I, row index matches the index here, I, and then the index j, the column index, starts out at I plus 1. In other words, it's strictly greater than I. And we go all the way to the end. And we multiply that by the corresponding unknown xj, which we have found previously, because notice this loop is going backwards. It starts from n, and then it keeps going, counting down all the way to 1. And then we do the division. So the idea is for you to convince yourself that the way this process can be implemented is by following this algorithm. So does anyone have any questions as to how this algorithm arises from this process? one thing we're pointing out, the very first time through, when I is equal to n, so we set xn equal to yn, but then j starts out at I plus 1, so j would be n plus 1. So now we're counting from n plus 1 up to n, but that can't happen because we're already greater than n. Therefore, this inner loop would not run the first time around. And then we do, so we just set it equal to the last right-hand side value and then only do the division, and then the first unknown is done. Only from starting from a second iteration do we actually start subtracting terms off, which is what we saw here. So this is called back substitution, back because we're going through the equations backwards. So this is how we solve a upper triangular system. Okay. Now, this is more expensive than solving a diagonal system, which required only n operations. This requires order n squared, which you can see from the 2 levels of loops that we have here. This loop can run as many as n minus 1 times. This loop can run as many as n times. Well, actually, it runs exactly n through n iterations. So it turns out that the number of operations, so these subtractions, these multiplications, these divisions, if you add all of that up, it turns out to be exactly n squared. So when n is large, this takes a whole lot more work than solving a diagonal system. Now, I won't talk much about lower triangular systems just because it's not really much different from upper triangular. So this is a structure that it has, and so you can see that if you start from a first equation and work your way down, using a similar process, then you can solve a system, and again, order n squared operations. So that process is called forward substitution. We will deal with forward substitution a little bit later, like when we get to the next section. We just don't really need it right now. So we have a way of solving certain simpler systems of equations, diagonal case, a triangular case. But now suppose we have a general square invertible n by n matrix A, and we need to solve Ax equals B. So how can we get that system to at least be triangular? And then we can go ahead and use, like, if we can reduce it to upper triangular form, then we know that we can use back substitution and get x that way. Okay. So what that means is if we can manipulate the equations in such a way that the solution is not going to change, that would give us a way to make the system simpler. Like if we can eliminate certain entries from unknowns from certain equations, then that would bring us to triangular form. Because if you look back at upper triangular form, so here this first equation depends on all the unknowns. We don't need to do anything to that. This equation, we need to eliminate x1 from it. This equation, this last one, we need to eliminate x1 and x2 from it. So if we can do that, then we get this upper triangular form. So for that, we use what you learned in your first linear algebra class, elementary row operations. So you can scale an equation, so multiply both sides of the equation by a certain number. We won't really need that one very much. You can interchange the order of equations. We will need that from time to time. And then this is a key one right here. If we take an equation and replace it by itself minus a multiple of a different equation. So when we're doing everything to both sides of the equation, the solution is certainly not going to change when it's a linear equation. So, so we can, anything we can do from these types of operations to eliminate unknowns from equations will help us get to upper triangular form and still be solving an equivalent system. So here I have a made-up system of equations. So what can I do? What I like to do is I like to eliminate x1 from the second equation. So I can multiply this first equation by 3 and then subtract that. So the 3x1 here and the 3x1 here will cancel out. So x1 will be eliminated from the second equation. And then just carry out the rest of the subtraction of both sides. And this is what I get. So x1 is gone. I can do the same thing to eliminate this x1. I can multiply the first equation by 4 and subtract. And that'll get rid of the 4x1 term here. It'll cancel out. So now I'm getting closer to upper triangular form. So, oh, typo. Well, good thing I'm actually in edit mode here. That should be x1. Oh, great. The thing is, any typo I find here, that means it's a typo in the book. Ugh. So I'll have to add that to my steadily growing list of errors that I post on my webpage. Dang it. Okay. So then, oh, it's interesting how it only there, not there. Okay. So now I want to eliminate x2 from the third equation. So if I could just subtract these two equations, then the minus 4x2s will cancel out, and I only have this. So now I have this upper triangular structure. So I needed to remove x1 from every entry in the first column below the first one. I needed to remove x2 from every entry in the second column of a matrix of a system below the diagonal. So now it's upper triangular form. This is actually the system that we had earlier. So now you can just use back substitution and solve it. Okay. So to formalize this process, we need to work on both sides of the equation. So we form what you learned in linear algebra was the augmented matrix. So we have a matrix A here, and then we just slap on B as an additional column. So now we can just work with these entries instead of writing the equations out every time. Now we're trying to get this to upper triangular form. In linear algebra courses, it's referred to as row echelon form, not reduced row echelon form, just row echelon, or maybe just echelon form it might be called. Okay, but it's probably been quite a while since you've taken that class. So to systematically eliminate whatever entries we need to get to upper triangular form, that process is called Gaussian elimination. And it's interesting that it's called Gaussian elimination because Gauss, Carl Friedrich Gauss, one of the greatest mathematicians of all time, he has a lot of things named after him, but he did not invent this process. I'm not sure how Gauss's name got attached to it. There's records of these operations being performed, thousands of years ago, so long before he lived. But Gaussian elimination is what we call it for some reason. I don't understand it because he's got so many things named after him that are legitimate, but whatever. So what I want to do is carry out this elimination on a system such as this one. So if I extract from this system the coefficient matrix A from whatever's multiplying the x's, and then the right-hand side B, and then I put them together as an augmented matrix. So this is a matrix, A tilde, that I'm actually going to work on. So the first thing I want to do is I want to zero all the entries in this first column below the 2, because that will eliminate x1 from these second, third, and fourth equations. So if I can find the right multiple of a first row, just a first row, to subtract from each of the other rows, then I'm making progress towards upper triangularity. So I have here subtracting 3/2 times the first row from the second to zero out this entry. Why 3/2? 3 is the entry I want to eliminate. 2 is the coefficient of x1 from a first equation. So it's the entry on the main diagonal. Because if I multiply this first row by 3/2, then this 2 becomes a 3. that will then cancel with the 3 when I subtract. So that's the multiple of the first row that does the trick. Excuse me. And then I keep going. So here I want to get rid of a 1. So I multiply the first row times 1/2. 1's the entry I want to eliminate. 2's the diagonal entry from this column. So that does it again. Here I want to get rid of this 5, so I multiply the first row by 5/2. And then subtract that from the fourth row, and then everything in the first column below the diagonal is zeroed out. So I've eliminated x1 from the second, third, and fourth equations. And now I can move to the second column. Now the numbers are not working out nicely, like in previous examples, but it's a computer doing all the work anyway, so it doesn't matter. So here I want to I keep this entry. I want to eliminate this one and this one. Only entries below the diagonal, because that's what I need to get rid of to make this upper triangular. So if I have 3/2 divided by -9/2, that's the multiple of the second row now that I subtract from the third. And then I have so -15/2 divided by -9/2, that's 5/3, times this row subtracted from this row gets rid of this entry. So then I keep, and then I'm almost there. I just have to eliminate this one last entry in the same manner. And now I have upper triangular form. So now I have this 4x4 upper triangular matrix, and this is my right-hand side, which has changed as a result of all these row operations, because you had to work on both sides of the equation. And now I can solve this system using back substitution. And then I have my my x. So now we just need to formalize this process because now we know what ratio to multiply each row by to subtract it from other rows and eliminate entries. So we examine what we've just done. Notice in this example, we needed to look at the first column, second column, third column, not the fourth column. Why? Because there's nothing to eliminate. There's nothing below this entry. So our outermost loop, we will examine column J from 1, 2, 3, up to n-1. So that defines our outermost loop. So then within this loop, we're going to examine column J and eliminate all entries below the diagonal. So these are the entries that we need to zero out. For each column J, I starts at J plus 1. So I has to be strictly greater than J. Remember from the definition of an upper triangular matrix, Aij is 0 whenever I is greater, strictly greater than J. So that's why this J plus 1 is our starting point. So that defines our next innermost loop. So we have a system of nested loops where our goal is to eliminate Aij for this I and this J. But the elimination process involves performing a row operation. So we still need to update the rest of that row. So we're eliminating Aij, but if we go back to the example, like for example, when I use the second row to work on the say the fourth row, I needed to get rid of this -15/2, but then look at these two entries. These entries, of course, are going to change because I'm taking a multiple of this row, the second row, and subtracting it from the entire fourth row. So this entry, and then this one from the right-hand side, all of those have to be updated. This one, I know it's going to happen. It's going to become 0. So this is how the algorithm results. So I iterate over all the columns, except the last. For each column, I start below the diagonal and I go all the way to the bottom. So in here, if I highlight this part here, all of this, the job is to perform a row operation that zeroes out aij for this I, whatever I is equal to and whatever j is equal to. And what is that row operation? We're taking a multiple of row j and subtracting it from row I. What's the multiple? That's right here. The entry we're trying to get rid of, aij, divided by the diagonal entry in that same column. So that's ajj. This is called a multiplier. That term will come up later on. Now, performing a row operation, we start to the right of the entry we want to eliminate, and we carry out the row operation. So each entry is equal to itself minus the multiplier times the same entry in row j. So here we have row I, column k. It's being updated by row j, column k. And we multiply that by this multiplier. And then we're subtracting. So this performs a row operation. And then we do the same thing to the right-hand side. Same ratio times the entry from row j, affecting the entry in row I. So now we handle the entire augmented matrix. And that's it. Once these row operations are done, then we have our upper triangular system. Now, one very important point that this comes up in homework. Notice I don't actually do anything to aij. My column index starts past that point at j+1. Why is that? Well, I mentioned earlier, we know what it's going to be. aij is going to be 0. If we know it's going to be, then why do we actually have to go through the trouble? Why do we perform floating point arithmetic operations for which we know the results? So we just skip it. Now, this becomes an issue in the homework. Like when you have a homework problem, which you will have, where you implement this, you write a Matlab function that does this, then you try it out on a matrix A, and you're thinking, oh, my code isn't working because the matrix I get out is not upper triangular. Well, no, it's not, but that doesn't mean your code is wrong. All it's doing is the upper triangular part of your final matrix is correct. It's leaving stuff behind in the lower triangle, of those entries aij that are supposed to be eliminated, but they're just not actually explicitly set to 0. They don't need to be. Every operation counts. We don't want to do operations that we don't actually need. Certainly not for large-scale problems. So that's why it's skipped over. So just keep that in mind when you do homework on this. That's not going to magically produce an upper triangular matrix. If I set this index k equal j+1 up to n, then it would do that. But again, it's wasteful. Now, how expensive is this algorithm? We have 1, 2, 3 levels of loops, whereas back substitution had only 2, and then solving a diagonal system had only 1. So this is a more expensive process than either of those two. So it turns out to be order n cubed, because this loop runs n-1 times, this loop runs as many as n-1 times, this one too. So it adds up to order n cubed operations. Roughly 2/3 n cubed operations. So I'm going to fill that in here. And typeset that in a less confused, ambiguous way. Okay. All right, and that's what I was just talking about here. But it's not necessary to explicitly zero the entry. Okay. Oh, wow, I've come to the end. I honestly didn't think I'd make it through all this stuff. It seemed like too much. Okay, so so now we have an approach to solving AX equals B for a general invertible matrix A and right-hand side B, where we carry out this process to reduce A to upper triangular form, and this will also perform the same row operations on B. So after you do all this, then you can call back substitution on the output matrix A in a modified vector B and get the solution to X equals B. Now, yes, you have all this junk left in the lower triangular part, things that you did in 0, but the algorithm for back substitution never accesses that part of a matrix. So it doesn't matter what numbers you have in there. It's not going to affect anything. It'll still produce the correct result. Okay. All right. All right. Any questions at this point?
I have a question.
Yep.
Okay, so how do you talk about the algorithmic complexity? I know you've explained it before in 561, but I still can't figure out how to get the exact 2/3 n cubed.
Oh, okay. So why is it 2/3 n cubed? You're asking?
Yeah. Like,
okay.
How do we calculate, not just for this, for let's say for an algorithm we write, how do we calculate algorithm complexity?
Okay. All right. Actually, this is a good way to fill the last 15 minutes. Okay. So, so here's how you do it. If you start from the simplest statements, like these statements that perform computations, and you see, okay, how many operations are involved in each one? So, for example, here we have 1 subtraction and 1 multiplication. So we have 2 flops. Flops is short for floating point operation. This is floating point arithmetic. So, so we have 2 flops performed per step. Now,
so we're starting from the innermost loop.
Yes. Yeah, because you're trying to count floating point operations. So if we start with those statements where floating point operations are actually performed, there's your starting point. So like here we have 1, and then here we have 2 more. Okay, but now where things get complicated is where you deal with loops, especially loops that run a varied number of times. Like here, this loop always stops at n, but it starts at j plus 1. So what we can say, though, is that this innermost loop runs 2 times n minus j flops. Okay, so for whatever j is. So now, if we look at the body of the loop, okay, and add everything up, I have the interior of a loop would be 2 times n minus j plus 3. So these 4 lines carry out this many. Now it gets more challenging, though. Now I want to see how many floating point operations does this loop perform. So I'm going to figure that out down below. So I can express this as a summation. It'd be the sum I equals j plus 1 up to n of this total here. Okay. So now I need to figure out what this sum is. Now I can break this down a little bit. So
I'm sorry, hold on. So in the second loop, the line where we had the multiplier, why do we have plus 3 flops? Like
Okay,
we're just doing division, right?
well, I have yeah, so I have these, and then the 1 here, and then the 2 down here.
Oh, okay.
Okay, so actually, here I've I going from j plus 1 to n, so that also will become n minus j. So I can figure out, so because this loop runs n minus j times, in fact, you have these 2 loops, both run n minus j times, so I could get this part here and then this part over here. And you can see here we have 2n squared, so now we're doing order n squared work so far in this second loop. But now what about this? Well, to evaluate this, I need my summation formulas. Like this one. And for this particular algorithm, we will also need, eventually,
Small squares.
Yeah. Okay. So you can figure out this sum using this by summing from 1 to n and then subtracting off a part, summing from 1 to j. So you're going to get a pretty ugly expression in here that will depend on n and j. But then whatever you get from this, okay. Whoops. Yeah. Then you're going to take that, which is a function of n and j, and sum it from j going from 1 to n minus 1 to get an expression that will involve only n. Like notice here we have this is going to be n. The leading term of this expression is going to be n cubed over 3. And notice here the leading term in the number of operations is 2n. So once we take these other loops into account, that gives you an idea of how the leading term turns out to be 2n cubed over 3 from these 2 operations performed in this loop. And then you're going to have other terms that are lower powers of n that we tend to neglect. But you get the idea here as to how you proceed. Yes, it's quite tedious. But these are the tools that you use.
Okay. This will be posted on the page, right?
Yeah. Yes, I'll be posting this.
Okay. I might need to look at this again.
Yeah. Well, yeah. Go ahead and give it a go and see if you get the correct result of 2/3 n cubed plus other things.
Okay.
All right. We still have some time. Are there other questions? I see things popping up in the chat. I'm eagerly anticipating. Best resource refreshing. Okay, first resource for refreshing on MATLAB. Okay. Well, there's always the tutorial in the book. That was chapter 1. That if you go through those, I'm going to point out another one that's actually posted on the site, I believe. Yes, this. This is my friend Margot, who some of you saw. I got to see in Teams last semester or in Zoom. She wrote a MATLAB tutorial that you might also find helpful. And there's MATLAB comes from the MathWorks, and that's and I believe they have, if you go to their site, mathworks.com, but they have various resources also for getting used to MATLAB again. Okay, now okay. So this is my dog, Biscuit, and I am so embarrassed. I don't really know my dog breeds very well, and you are the third person to ask, and I'm like, so I know a few breeds. The last dog I had was actually a Pekingese, and that was over 20 years ago. So if someone wants to embarrass me further and tell me what breed this looks like, then by all means. And otherwise, I'll take a look at her vet bill, and maybe it says there. So. Okay. But yeah, I think enough people have asked that I really need to have an answer for this. Okay. So, alrighty. And yeah, actually, that's the only picture I have of her too. Well, I'm sure Dinah has plenty by now, so I'll have to get those and put them up to go with the cat's page, which I guess now I have to label in memoriam. So, all right. But it's been quite a wild time lately, but it's always good when you have something furry in the house. So, okay. In the last whoops. Okay. In the last 4 minutes, any other questions? Oh, I see everyone coming in chat. Oh, right. I should be able to, like, my schedule gets really full because I have lots of meetings with research students, and took a while to get that schedule ironed out. So now that it has been, I can see what gaps there are and have some office hours. So I'll make an announcement about that on Monday, or put something in Canvas as to when my office hours will be.
One more question. So if I understand correctly, the grades for this class are just the 10 homework problems. There's no exam, no project.
Right.
Okay.
Yeah. Okay. One thing I've done in the past, I haven't put it on the site for the. I do have an assignment as a programming project where it involves implementing one of the algorithms that I will cover for computing eigenvalues of a symmetric matrix, where you have the option of doing that instead of one of the regular assignments that are currently posted. Last time I taught the class, not many chose to go that route, which is a little disappointing. But yeah, I'll probably put that out as an option for this time. So that way, if you're really tired of doing proofs, because there will be some, and you'd really rather code. Well, I don't think we made too many people in that category. Oh, okay. Then okay, so maybe there'll be at least one person choosing that. Okay. Well, pretty much coming to the end of our time here, and then well, several of you I will see again in 15 minutes for 517, along with a bunch of undergrads. So that'll be interesting. So I'll see you again for this class on Monday, and I'll get this posted sometime today.
Thank you, Dr. Lambers.
Mm-hmm.
Thanks. Thank you.
Yep.
Okay, so I have a quick question just because I forgot, and you might have this sitting in front of you. Do you remember what time we set our meetings for Friday?
Oh, hold on. I'm going to stop recording.
Because I thought about that today and I was